Today we're going to finally dump the keyboard and serial terminal and build a monochrome video card so we can finally play some games with our EUP5108 microcontroller. I'd really like to be coding my own version of Tetris or Breakout or maybe even Pong. So today we're going to explore what it takes to build a small, low-resolution monochrome video card, much like the TLA display that I built in TinkerCAD some time ago. But first, some great news for the channel, as we have picked up a new Pateron. Chris, thank you very much for joining us. And we're celebrating 2 years with our patron Ian. Thank you both so very much for your support. It is greatly appreciated and very encouraging. If you'd like to join them as a patron, just scan this QR code. All of our patrons get full access to the 5108 support files for Logisim, including a detailed user's guide, the assembler, all of the EUP assembly source code that we've been using in this series, and also the ROM files. And remember to please like, subscribe, and ring the bell for notifications so you never miss an episode as we once again take a dive into the deep end of computing with the EUP5108 virtual microcontroller. So far in our experiments with the EUP5108, we've used it pretty much like an 80s PC with a keyboard and a serial terminal. And while the creator of Tetris first developed the game on a text display, our refresh rate is just too slow for the game to be playable. And in addition, we can only fill the screen from the top down. We can't individually address characters and move them around. So to build our pixel display, we're going to start with an 8x32 LED matrix. And the LED matrix works by enabling both a row and a column for each individual LED that you want to turn on. So if we track through this circuit, what we see is first a clock, a row counter that counts from 0 to 31, and then just cycles around. The 5 bits of the counter that come out are then fed into a decoder, and what the decoder does is break out each of the values of the 5 bits coming in into separate wires. So we have 32 wires that feed into the row selector of the matrix. The column selector of the matrix is represented by these dip switches. So as you can see, the first row is turned on here by default, since the value of the counter is 0 at the beginning. And if we turn on any given column, you'll see that the corresponding LED is lit up. Each time the clock increments the counter, we go down 1 row in the matrix. And if we want a different pattern for a given row, we have to provide a different set of column values. And obviously we're not going to make much of a display doing this step by step. So if we let it run, what you see is the row values just sort of jump around, and then what is happening is the LEDs are only lit for the very brief time that both the column and the rows, or rather the column and the rows, are enabled. To make this a little stickier and allow the LEDs to glow, much like the points in an old school CRT, we have to adjust the light persistence value. And now, making the light persistence value 32 for the number of columns, we get some persistence, but it's not enough, because what we need is the light to stay lit until we come back around and decide whether or not to light that row again. So to do that, we need a full 64 ticks, and then we have a stable display. Now, to make an image, we just need a way of storing our separate column values, one for each row, in a block of video RAM. Now we have a timer going to the counter. Just as before, the row counter feeds both the address of the RAM as well as the row select. As each row is enabled, the appropriate column value is displayed. So what we've done is rearrange the decoder so that it now goes from bottom to top rather than top to bottom. And then we have this sort of odd wiring group here. This is essentially an Indian swap in hardware, where we swap the order of the columns so that these columns line up with the display itself. single step through this a bit. We draw the individual lines, but it doesn't quite look like what I intended. So let's let it run. And you can see it's sort of an image, a little unstable. Let's take a look at why it's unstable. We'll go back to the start. Pattern is AA, which is 8484 on the individual bits. And then if we cycle one time, we get 55. Now 55 should be 1414, and this should look kind of like a checkerboard. And that's actually the reason why I use this pattern, is to be able to readily see what's happening in the display. What it appears is happening is that every time we go to change rows, we're actually outputting the previous value in RAM as the new row comes up. And that is causing a mix of the two rows. So 55 mixing with 0 is actually 55. We then get the 22 clean because 0 and 22 is clean. Now we go back to 55, but as you can see, both 55 and 22 are represented in this line. So if we go ahead and run this like we did before, we get something of a display, but you can see the flickers in between, and that's because we have a bit of a race condition going on. But we can handle that by adding a buffer to the data output and enable that buffer only when we're not changing the row counter. And that is this circuit. What we've done is we've added that buffer, as I mentioned before, and then when the buffer is disconnected, we have a pull down resistor to make sure that the output is 0. That way, every time the counter counts and goes to another row, we are effectively combining it with a 0 instead of the previous value. So as we draw each row, we see that we begin to get an actual picture. Let's let it run. And sure enough, there's our image, EUP5108. Except that the E is just a little off. And that E, this line here in the E, is this byte in RAM. So if we change that to C0, we get our correct image. Now, of course, we don't have a way of manipulating RAM like that when the system is running. What we need to do is connect up the write enable and the data lines, and then that way we'll be able to change the RAM from the processor. Putting it all together, we have a new circuit. In this case, we have a timer tick, which goes into a sequencer counter. The sequencer counter counts from 0 to 3 and back again, and controls the access to the various bits of the video card. So the sequence begins with the buffer enabled and the output of the RAM being displayed on the first row of the display. Going to the next stage, provide an output from the sequencer to increment the row counter. While we're doing that, the output is disabled. That row counter increments the address in RAM and the row select decoder, much like our previous one. The next step is to switch the address multiplexer to the address that we wish to write or update in RAM, and give that a chance to operate if we are in the middle of a write instruction. The next step of the decoder actually clocks the RAM so as to load whatever data we had just set up. So if we let this run, we get that same display as we did earlier with our messed up E, except now we want to change this location. We can do so by selecting the address of that location, changing the byte that we want to put in, and providing a write enable. So that allows us to update the video RAM from our microprocessor, and do so in a synchronized fashion so as to not upset the display. And that's pretty much all there is to a basic 1 bit per pixel display such as this. As you can see, we use very little RAM using 1 bit per pixel, kind of output we can expect from a simulated microprocessor. As I mentioned previously, I have the 2 different row outputs so that I can mount the display horizontally, and we can sort of have a banded display using multiple video cards. We can expand our display to multiple sizes. In fact, since the EUP has an 8-bit output port, and we're using 5 of those bits for the row address, we have 3 bits left over, which would allow us to build up to 8 of these stacked on top of each other, assuming we had the resources to run that kind of display. I believe if we do 3 of them, we get a reasonably decent sized display. 2 is a start, and that's where we'll start next time, connecting the EUP up to this display so that we can actually change our message. That's just about all I had for today. Like I said, like and sub for more, you know the drill. And we'll be seeing you next time once we finally connect this to our EUP and perhaps have some sort of game to show for it. Bye. Today we're fun that run in Logisim with the attached keyboard and serial monitor. Jesus, I can't speak today.